a empezar, disculpen que se nos hizo un pelín tarde. Hoy no tenemos a Sven Heinemeyer, que creo que muchos de ustedes lo conocen bien porque es de la casa, es de FisPyC, y accedió a darnos este seminario hoy. Espero que se repita en los siguientes años, ¿por qué no? Él estudió sus estudios de undergrado y los hizo en Karlsruhe. Ya entonces ya estabas con Higgs, ¿no? Era Higgs a dos As, ¿no? Sí. Y después hizo el doctorado también en Karlsruhe y la habilitación en el Ludwig Maximilians University de Múnich. Y después fue postdoc en Karlsruhe y después fue fellow en DESY, en Brookhaven, en el CERN, en la división teórica. Obtuvo una Ramónica Hall en Zaragoza y en el IFCA llegó en el 2006. En el 2007 fue ya científico titular del CSIC. En el 2010 fue investigador del CSIC y en el 2016 pasó a una estancia en el IFT de Madrid, en el Instituto de Física Teórica, donde también es profesor de la UAM. Y en el 2018 ya se convirtió en profesor de investigación. ¿Sí? Su carrera es muy extensa y además es un gran experto, como creo que todos aquí sabemos, en supersimetría, entre otras cosas. Así que nos va a dar una charla de por qué el modelo estándar no es completo, no es suficiente. ¿Todo bien?
¿Qué pasa?
¿Sí?
A veces funciona, a veces no. Me ha pedido que hable en inglés y las transparencias también están en inglés. Si tenéis preguntas podéis hacerlos en español también, ¿no? Y también, a veces no sé si sirve para... A veces aparecen preguntas en un color distinto en español y quizás alguien quiere comentar una respuesta. Okay. I was asked to say something about the model that we are currently working with in particle physics, the standard model, and why, not only likely, but certainly we have to go beyond it. And therefore I called the talk, why the standard model is not enough. I will first discuss in very simple terms, because I also understand that this has not been discussed very deeply so far, the standard model, and in particular its Higgs boson, its Higgs sector. I will talk about the shortcomings of the standard model. I will tell you how my favorite theory, supersymmetry, comes to rescue. And finally, I will answer the question, is SUSY dead? But we know already, if such a question is posed, the answer is always no. The standard model of electroweak and strong interaction. This is the theory that describes all the particles that we know and its interaction at the microscopic level. And it's a quantum field theory, meaning that the interaction between particles is given by the exchange of a field quantum. And this is depicted here, for example. You have an electron, you have a charged nucleus, and the electromagnetic force is given by the exchange of a photon here, or also called a nu. And this is an example from quantum electrodynamics, the very simplest example. And without going into too many details, but to introduce the necessity of the Higgs sector, of the Higgs boson, the building principle of this type of field theories are so-called gauge transformations. Meaning, we have our Lagrange density, where all the fields and particles are described with the interactions. And then we perform a gauge transformation, meaning, for example, we have here a fermionic field, and then we shift it with this factor here. This is our gauge transformation. Then also the photon field is shifted by this factor, and always this lambda of x enters. And you can do this, everything works out, but if there was a term like m squared nu, which would be a mass term for our photon here, this term is effectively not gauge invariant. Yeah? You apply this gauge transformation, and you see that the Lagrange density changes in the end. So we are not allowed to write down such a term. And luckily, the photon is massless, so we don't need this term. I mean, experimentally, we know that it's all the tests have shown it's massless. From the theory, it's constructed to be massless. We don't need such a term. Everything works out. So our photon is a massless gauge field. Perfect. Now comes the problem. Well, no, one slide more. This was the original idea of the gauge transformations. Just to show where we are, these are the elementary particles that we knew as of 2011. We will see how this changes. So we have here our quarks. These two make up the protons and the neutrons, and then the second and third family. These are the leptons, electron, and the neutrino from the first family, and the muon and tau, the third family. And the force carriers, the photon, the gluon for the strong force, the Z boson, and the W plus W minus boson. As I said, all have been eventually seen. Many of those received their own Nobel Prize when they were discovered. But, as I said, this theory, by construction, predicts massless gauge bosons. So all these particles here, they should be massless. Now what happens? You do the experiment, you find out that in fact these particles are not massless, they are massive. And this poses a problem. It's not clear how to incorporate this kind of particles with their mass into the Lagrangian. Yeah? So the explicit mass terms, like this m squared a mu that I was mentioning before, breaks gauge invariance. And people were thinking for many, many years how to solve this. Many proposals were made, and the proposal that worked out best in the end, and well, the only proposal that really worked out in the end, is the so-called Higgs mechanism. I think I should politically correctly write here Brout-Englert Higgs mechanism, because the mechanism is, I think, officially called after these three gentlemen by now, but for short Higgs mechanism. And the Higgs mechanism in principle is very simple. We write down everything as it is, no mass terms at all, and we add one new field. We add a scalar field, and the mass terms, and I will show you how this works out in a moment, they are created by the coupling of this field to the other particles. As I'll show you how this works out mathematically. Yeah? And in the standard model, it's very simple. We have one scalar doublet. It's a complex doublet, so here two entries, complex meaning 4 degrees of freedom. Yeah? We add this new scalar field with 4 degrees of freedom. We can write down the Higgs potential, and we have only one doublet, so it looks particularly simple. It has only a quadratic term with a prefactor mu squared, and it has a quartic term with a factor lambda. Now, lambda must be positive. Yeah? Otherwise, at large values of the field, we would go down to minus infinity. There would be no stable solution. The world couldn't exist. So lambda must be positive. But for mu squared, there are two possibilities. Mu squared can be positive or negative. And I mean, this we know from high school. If we would write down with a positive coefficient, then we would get a potential of this form here. Yeah? Nothing special, but it also doesn't help us. But if we choose by hand that mu squared is negative, then we get this shape of the potential. And the minimum of the potential is now moved away from the origin here, and this is the so-called vacuum expectation value, the minimum of the field away from zero. Yeah? And we can calculate where the minimum is located, etc. Now, why does this help us? Well, let's look at the Lagrangian again. Well, first of all, the Higgs doublet that I wrote down here, if we go, without going into too many details, if we go to a special choice of how to write it down, we can remove these other degrees of freedom, and we are left with only this V, yeah, this V here in the field, plus one elementary scalar field, which is our Higgs boson. In technical terms, it's called the unitary gauge, but I will not go into detail. So this is the simple picture how to write down the Higgs field after it shows that we have this the minimum away from the origin. And now we look at the Lagrange density. And this is a very simple Lagrange density of the Higgs field, which is also, by the way, depicted in the last two lines of my t-shirt here. You can buy this at CERN. I don't get any money from making this.
You should.
I should, I know. This is the kinetic term. Yeah, we have our derivative times the field, the Hermitian conjugate, times, again, derivative of the field. This is the normal kinetic term. We'll look in a moment. We'll see in a moment how this looks in more detail. Then here we have the coupling of the Higgs field to fermions. This is the SU2 doublet depicted here with the UL and the DL term and the DR term, so the left-handed parts and the right-handed part of the down-type quark, and something similar, I'll come back to this in a moment, for the up-type quarks. plus the Higgs potential that I've depicted on the previous slide already. But look, let's look at the first line here. These derivative that we have here, I spelled it down here in more detail. It contains the normal covariant derivative, but it also contains here the gauge bosons or the gauge fields, the W and the B, which later via mixture can form the W plus, W minus, and the Z boson. Now, this shows already everything that we need to know. We see here, for example, this phi contains a V, meaning here we have gauge boson V, gauge boson V, and this is exactly like we had before, a nu and nu m squared. We have V squared W mu, a mass term for the W bosons, or for the B bosons, and then they can mix, as I said, to give rise to the Z, etc. Yeah? But this exactly gives rise to the mass terms of the gauge bosons. And I've written it down in a slightly more mathematical form on the next slide, as we can see that it really works out. Let's have a look at this piece here. So here we have the Higgs field, phi, and it couples to this QL, which is given here, and you can see the VEF is downstairs, meaning the F is multiplied with the DL, not with the UL, but only with the DL, and then we have here a term DL, V, dr. Again, this is a mass term for the down type fermion, and I will show you again in a moment how this works out in a more mathematical way. Now, we also want to give masses to the up-type quarks, of course. How do we do this? Well, there's a little trick that we play. We form this combination. We take the complex conjugate of the Higgs field, we multiply it with the second Pauli matrix, which is 0, I minus I0. And this exactly flips the entries of such a doublet, meaning, or of such a doublet, and this moves the VEF upstairs. So this phi sub c has the VEF upstairs. And now it's obvious we have here the UL times V times UR, and this gives masses to the uptype quarks. Yeah? So the gauge invariant couplings to the gauge fields are shown here, and the mass terms for the gauge boson fermions are formed here and in this line. I have this slide showed slightly more mathematical, but I think it's a very nice view to see how it works out. We start out with a massless gauge boson, and if you do quantum field theory, the propagator of a massless gauge boson is just 1 over the 4 momentum squared, 1 over q squared. So this is this massless gauge boson. But now comes the coupling to the Higgs field, meaning twice the VEF, yeah, you see here, 1 VEF, 2 VEF, twice the VEF, always together. So in this piece here we have first the massless gauge boson, then we have this coupling, and again massless gauge boson. But we live in a quantum world, so this does not happen only once, this can happen twice, 3 times, 4 times, etc., meaning we have here this infinite sum. Now we write it down. So this massless field goes to the massless field, shown here, and then we have here again massless field, this piece, the coupling with the V squared, and the massless field shown here. And this with the power j equal to 1, j equal to 2, j equal to 3, etc., etc. This is this infinite sum. And this is again high school knowledge. This is just a geometric series. And if you sum it up, you end up with 1 over q squared minus m squared. And this m squared is given by this coupling squared, this one here that enters here, times VEF squared divided by 2. So this is exactly the propagation of a massive gauge field with the mass m squared. And one can see already one very crucial point here, namely the mass of the particle that we are looking at is proportional to the coupling of this particle to the Higgs field. Yeah? This is one of the crucial predictions, that the mass is proportional to the coupling to the Higgs field. And when we will come back to this when we want to test the Higgs sector. Yeah? But this is one of the crucial predictions that has to be fulfilled, has to be tested experimentally. I skipped the part for the fermions. It's the same construction principle with this infinite series, where we construct the mass of the fermion, which is given by the coupling constant of the fermion to the Higgs field, and again the mass is proportional to the coupling of the fermion to the Higgs. Very important prediction. Finally, we also have in the potential the self-coupling of the Higgs. Yeah? We have this phi to the 4 term, and you can imagine two of these phi's, we take the VEF, and the other two phi's are just the Higgs field, and then we're left with Higgs, VV. The coefficient was this lambda, and this is exactly a mass term for the Higgs field itself. Yeah, and the mass is given by this combination. I wrote down here 3 parameter, but it was the last unknown parameter of the standard model, which of course by now is measured. We'll come back to this in a moment. And this is what I wanted to make clear. Establishing the Higgs mechanism is not only finding this particle, but to measure all its couplings. Yeah? This is crucial in order to check whether all the properties of the particle that we've found really corresponds to the prediction of the standard model. And I had 2 questions here, but maybe we try to keep them in mind, and if you're interested, we can discuss them later, or you can think about them yourselves. Yeah? So, ¿cómo se puede medir los acoplamientos? How can we measure these couplings? You have an idea? Yeah? You can think. What do we do in order to measure a coupling? Well, how do you do it? And maybe there are more things that we should measure or test. Yeah? Not only the couplings. If you think of something, let me know. But these are 2 crucial questions, also for current LHC Higgs physics. Good. One more nice feature that, at least for me, made me believe in the Higgs mechanism before the Higgs discovery. Yeah? And this concerns with the process that I wrote down here, WW goes to WW. Yeah? You just imagine you take 2 W bosons, they scatter and they produce again 2 W bosons. And then you can write down the diagrams, and I've written down here, for example, 2 W bosons, they form here the photon or a Z, and then again you get 2 W bosons. Or like here where we have the exchange in the T channel, or we also have a quartic coupling between 4 W bosons. Now, if you calculate the amplitude of this process, we find that it goes like minus g squared, the coupling constant, times E squared, the energy of the 2 W bosons, divided by mW squared, plus terms that do not grow with the energy. And you may say, okay, why not? This is how it is. But why is this dangerous? Why is this dangerous? Well, the amplitude here is a kind of probability that this process happens. And we see that the probability grows with the energy. All the other pieces are constant. So the probability will grow and grow and grow. And at some point it will become larger than 1, and then the theory breaks down. It does not make sense anymore. So this is something that simply must not happen. Now, if you introduce a scalar particle to the theory, and we will see about the couplings, yeah? If you introduce a scalar particle, you get 2 additional diagrams. WW here with a scalar particle, which for some reason is called H. Give you 2 W bosons, or this exchange here. And then one can calculate the amplitude, and one sees they go with the coupling constant squared, this coupling constant squared, times E squared divided by mW to the 4th power. So we sum the 2 amplitudes, and then we see that this dangerous term disappears if this combination is 0. Yeah? And this is given for this combination of the couplings. And this is exactly the coupling that is predicted by the Higgs sector from the beginning. So the Higgs sector, or the Higgs mechanism as proposed, also solves this problem automatically without any additional ingredients. Yeah? And this, for me at least, was a very strong hint that there must be something behind. And I have one nice plot that I stole from a friend of mine who stole it from another friend of mine who is not related to the famous Engler. Yeah? It's a German guy, Englert. He's professor in Great Britain. And he made this nice plot where he shows the cross-section for 2Ws going to 2Ws. First, only with photon exchange. Yeah? Only this photon, and one can see it goes down and then it rises and the theory breaks down. Now we include more. We include the Z boson here and also this 4W interaction, and then it behaves better. But still, at some point it grows. Now we include the Higgs, here with a mass of 100 GeV, but this doesn't matter, and then everything behaves very nicely. Well, this is the mathematical or the graphical representation of what I've shown you before. So, this really works, and the Higgs sector makes sense. Good. Now, let's come to the big discovery. Yeah, this was the 4th of July 2012, and we were sitting exactly in this room here, I remember, where we had a live transmission from CERN, where these plots were presented, and I remember that even here we were applauding when they were presented. Of course, our CMS friends, they had seen them already before, I suppose, but at least the CMS plot, but this is also the Atlas plot here. And just to tell you, for the non-experts, what do we see in this plot? Yeah, this is the important question. So, here we have the mass of the hypothetical Higgs boson, and here we have what is called local P0, or local P value. This is the probability that what we see in our detector is caused by the standard model without any Higgs. Yeah, we take the standard model, we remove the Higgs, what do we see in the detector? What is the probability to see it? And here we see the probability is always around 0.5. Yeah, so here everything that we see is compatible with the standard model without any Higgs. But around 125, this value becomes very small. 10 to the minus 9 for Atlas, 10 to the minus 7 sorry, for CMS. And this means at this hypothetical value of Higgs boson mass, what we see can be caused by the standard model without a Higgs with a probability of 10 to the minus 9, meaning it's not possible. What we see here goes beyond the standard model without any Higgs and has to be tested compatible with the Higgs. Yeah, going below these values, 5 sigma, 6 sigma, this is called a discovery. Yeah? So here what we see can't be explained by the standard model without a Higgs boson. And luckily, the same was seen by CMS at about the same mass value, yeah, which is remarkable. Good. Now, we have a discovery. But what is it? Is it a Higgs boson? Is it the Higgs boson of the standard model? Is it a supersymmetric Higgs boson? We will come back to this later. Maybe some different model. I'll mention this in a moment. Those days also the so-called imposter theories were discussed, that we just see a particle that looks like a Higgs but has nothing to do with the Higgs. Could all be possible in principle. And the question is, how can we decide? And the answer is pretty clear. We have to measure the characteristics of this new particle, and we have to compare it to the predictions of the standard model and possibly to theories beyond the standard model. So we'll come back to this. And of course, what we also have to do is, in order to say whether it's the Higgs boson of the standard model or beyond, we have to search for additional Higgs bosons. And these searches, I'll mention this only very briefly later, they should, of course, you might think, if there are other Higgs bosons, they should be heavier. In principle, it can also be that the Higgs bosons below this 125 GeV that we just haven't seen. Yeah? One of my favorite topics these days is the Higgs boson at 96 GeV that CMS has seen, but Atlas is inconclusive. But this is, we can discuss this later. Yeah, so we have to search for additional Higgs bosons above and below 125 GeV. Yeah? So what we need in order to do this, we need precise predictions for all the Higgs boson properties. Now, let me just flash a few of the properties that are important for current LHC phenomenology and searches. Here, sorry, I've written down the various decay width. Decay width is the strength with which a particle decays into other particles. Yeah, so the strength that the Higgs decays to top quarks, to B quarks, charged quarks, or to taus, or to mu's, or to gauge bosons, etc., etc. Yeah. And then the so-called total width is the sum of all this partial decay width. Yeah, for our friends from CMS, this is what they do every day if they look at Higgs physics. Or at any other standard model type physics, I believe. But even more intuitive is the so-called branching ratio, which is the decay width in a certain final state, dd prime, divided by the total width, called branching ratio, and this is simply the probability. Yeah, we have the probability, which we can calculate, that the Higgs decays to top quarks, which is 0, as we will see. It can decay to 2b quarks, it can decay to tau plus, tau minus, it can decay to WW, etc. And there's a probability that each Higgs boson that you produce does this. Yeah, this is the branching ratio. And this is, maybe I skipped this. No, don't skip this, I'll come back to it later. This here was a plot that was produced, well, this version is from 2013. The first version was produced before the Higgs discovery, and therefore it was produced over a mass range from here 80 GeV to up to 1000 GeV. Because at those days when we produced it, we didn't know the mass. We had to be prepared for all the different values. And then you can see these bands, and they give the probability that the Higgs of a particular mass decays to a certain type of particle. For example, this is 100 GeV, and then the probability that it decays to BB bar is around 80%. Well, this is pretty clear. The width of the bands are theoretical uncertainties. As I said here, at 100 GeV it can decay to BB bar, for example. Then there's a probability of something like 9% that it decays to tau plus, tau minus, 7% to 2 gluons, 5% to CC bar, etc., etc. Then here's the decay to 2 photons or to 2 muons at the level of 10 to the minus 4. Now, on the right-hand side here, this, for example, is the decay to TT bar, to 2 top quarks. And since we know that our Higgs particle is around 125, we can see that it doesn't decay to TT bar because it doesn't have enough energy. That's pretty clear. The top quark weighs 173 GeV, and it's far too heavy that the 125 GeV Higgs boson could decay to it. But if you could choose which value of the Higgs boson mass you would like in order to do nice physics at your collider, which mass would we like to have? Well, of course, you want a mass that allows the decay to all the different particle species. Imagine you have a very low mass. Yeah? Then you have hardly any decays to the gauge bosons here. Yeah? This is it's so small, it's very difficult. You only have the fermions, and then maybe here blue or so, but you don't have the decay to gauge bosons. If, on the other hand, the Higgs boson mass is very high, like here, we only could see the decay, for example, here, we would only see the decays to WW and ZZ, but no decays to fermions. Also not nice. But at 125, which is incidentally also the maximum of this curve here, we have all the decay modes relatively large open that can be analyzed. Yeah? So nature was very kind to us. It realized the Higgs factor where it allows us to measure the Higgs boson with all the couplings to all the different particles. It's very nice. This is a zoom from 80 to 200, and again it's at 125 here. One can see, really nice. Yeah? All the different decay modes are open. Perfect. Good. This is just one slide to show you how a Higgs boson can be produced at the LHC. I hope you know that in the LHC we collide protons and protons, and the protons consist of quarks and gluons. So this may look surprising, but the largest production cross-section, largest probability to produce a Higgs, comes if we take 2 gluons out of a proton. Here the gluons form a triangle with a top quark, and then out of the top comes a Higgs. This is the largest production cross-section for a Higgs boson at the LHC. The second largest is this one here. We take 2 quarks out of the proton. The quarks emit either W bosons or Z bosons, and then those form a Higgs boson here. Also very nice. The third one is the so-called Higgs-Strahlung channel. Nice German word, Higgs-Strahlung. Where 2 quarks produce again a gauge boson, and then the gauge boson radiates the Higgs. And finally, what can also happen is that we take, that we produce 2 top quarks, and then the top quark, like here or like here, radiate a Higgs boson. Yeah, these are the relevant production channels, the relevant production modes of a Higgs boson at the LHC. And to show you, this is for 8 TeV center of mass energy, but it looks very similar for 13 TeV. So the current center of mass energy. Again, the clock that was produced before the Higgs boson discovery, therefore it goes again from 80 to 1000 GeV. See, this is blue going to Higgs. Then this here is this fusion of two massive gauge bosons. Then here the Higgs is radiated from W, here the Higgs is radiated from the Z, and here it's radiated from the top. And 125 we are here, and this is exactly the hierarchy that I discussed previously. Blue, WW fusion, and then the other channels. Very nice. This is how we produce the Higgs bosons at the LHC. Good. Now that I've convinced you that there's a standard model, that it works very nicely, and that we can analyze the Higgs boson at the LHC, I'll try to convince you that this model is not good. We will see about this. Yeah? Fact 1. We have a discovery. We've seen these plots. The discovery is there. Perfect, you think. Even more. I will not discuss this in detail. I leave to our experimental friends. The Higgs that we see is, in fact, standard model-like. Behaves in its couplings quite like the prediction of the standard model. This is one plot from Atlas, one plot from CNS, not the latest ones, but they depict it very nicely. You look at the various decay channels, for example, Higgs to photons, to ZZ, to WW, to BB bar, to tau plus, tau minus. Then we measure this kind of process where the Higgs decays to this channel. We divide it by the standard model prediction, and then 1 should be the answer. Yeah? 1 meaning we divide by the standard model prediction, and the measurements are all very close to 1. Here and also here by CNS, for all the various channels, they're very close to 1. So we have a standard model-like discovery, yeah, within 10–20% of which is the uncertainty that we have nowadays. The Higgs that we see behaves like the Higgs of the standard model. But there's a second fact, and this I will discuss in a little bit more detail. We know, and this is not a hypothesis, we know for a fact that the standard model cannot be our ultimate theory. And I listed some of the facts here, and I will go through some of them in a little bit more detail. First of all, we included 3 forces. Yeah? The electromagnetic force, the weak force, and the strong force. We did not include gravity. So something is missing. At the Planck scala, something will happen. Gravity is not included. There is something called the hierarchy problem. I'll show you on the next slide what is the hierarchy problem. But it's not solved by the standard model. As I said, 3 forces are included, but what we want in the end, we want to have a unified theory where all these forces become one force. And in the standard model, this does not work out. And I'll show you again how this looks like and what we can do about it. Yeah? Fourth, for our astroparticle friends here, we know that there's dark matter in the universe. Yeah? The standard model doesn't have any good candidate for dark matter. I'll show you how this can be solved. I was mentioning the neutrinos. In the standard model, the neutrinos are massless. However, we know they have a mass. Yeah? It would be possible to include a mass term. This would be very artificial because the mass of the neutrinos is something like 10 to the minus 6 smaller than even the lightest other particle in the standard model, which is the electron. Yeah? So it would create a very large hierarchy, which is very unnatural. So neutrino masses are also not easily to be included. And finally, there are a few, not many, but there are a few experimental results which are not well described by the standard model. And my favorite one is the so-called anomalous magnetic moment of the muon, and I'll come back to this in a moment. And I'll explain in 1–2 slides what this is. But there's one measurement that shows a persistent 4 sigma discrepancy, by now 4 sigma discrepancy from the standard model prediction. And one could list more reasons, but this is just one set that we know for a fact that the standard model cannot be the ultimate theory. So let me give you one more detail here, the hierarchy problem. For the ones that have not seen this, I'll have this one slide here, and it's also important to come to my favorite theory in the end. Let's look at the Higgs boson again. Yeah, and said here this is the free propagation of a Higgs, and in order to describe it, we have our propagator, and maybe you remember, for the gauge boson it was 1 over p squared minus m squared, and also, well, it says the inverse propagator is given by this term here. Yeah, I times the form momentum squared minus the mass squared of this particle here. But again, we live in a quantum world, and so quantum corrections always happen. Nature does it all the time, but we have to do it hand by hand to calculate it. And there's this quantum correction, for example, this loop where the Higgs disintegrates into fermions, and then they propagate a little bit, form again here the Higgs boson. Yeah, this closed loop of fermion, and the contribution to the inverse propagator is denoted by this symbol here. Yeah, you can imagine that this free propagation with the mass here is changed by this quantum correction via this term here. We can calculate it. I will not go into too many details. We can calculate this kind of contribution, and if we say that well, maybe I say this one thing. Here also, of course, momentum is flowing. Yeah, here the momentum comes in, then the momentum is flowing and momentum comes out, but we don't know which momentum is flowing around here because it's a closed circle. Again, quantum world means we have to make a sum over all the possibilities. And the sum over all the possibilities for a momentum that we don't know is an integral. Yeah, here we have to form the integral d for k over this momentum that flows around here, the momentum k. And if one writes it down and one says our theory is valid up to a scale lambda, for example the Planck scale, yeah, at the Planck scale gravity comes in, so our standard model can't be allowed or is not valid above the Planck scale, we can take this value capital lambda, and if one calculates it, one finds that this correction here, coming from this loop, goes like lambda squared. So this correction is proportional to the upper limit of our theory of this mass term squared. Now, we know by experimental measurements that this is 125 GeV or so, and this, if this is the Planck scale squared, yeah, this gives us a correction that is something like 10 to the 30 times higher than the original mass. And we have to take care of this. There can be cancellations, but to have a cancellation over 30 orders of magnitude is very unnatural. Yeah, so the problem is there is no symmetry that protects zero or small Higgs boson masses. There's no protection against these large corrections, and therefore the correction in principle could be or should be as large as the scale where the standard model becomes invalid, which could be the Planck scale in this case. So this is one of the problems, the so-called hierarchy problem between the Planck scale and the electroweak scale where we live. We come back to this a little bit later. Dark matter, just one plot here. It's also not the last one, but it's the nicest one that I've always seen, yeah, because it combines the three measurements, and I'm sure that our astrophysical friends can explain this much better than I can do. This is the plane of the density, energy density in the universe. This is the matter density. This is the what we now call dark energy density. And the sum one is this one corresponding to a flat universe. There are several measurements from the cosmic microwave background, from supernovae and from clusters. They all meet in this one point here, and if one does this, the numbers more or less look like this. The total energy density is about 1, so we have a roughly flat universe. But if we calculate it, if we see how many stars, how many gas is there in the universe, we find out that the matter density that we get from this plot here, the matter density, does not correspond to the visible matter. Yeah, there is a mismatch between the stars and the gas, etc., and what we infer from this kind of analysis here. Meaning, first of all, we have a substantial contribution from the dark energy, but we also have something like dark matter that is visible only via its gravitational interaction. And the problem is, within the standard model, there's no candidate that can give us this kind of dark matter. It's not possible. Yeah, people were thinking in the beginning whether the neutrinos might be able to do it, but there are several problems. First of all, the density is not high enough, and second, they don't behave correctly. Yeah, they are, let's say, too relativistic in order to correspond to the structures that have formed in the universe. So the standard model can't explain it. This is one of the, for me, it's the clearest indication that we need physics beyond the standard model. Yeah? So dark matter tells us we must go beyond the standard model. And fact number 6. So I had 6 facts. This I explained the hierarchy problem. I said something about dark matter. And this is the experimental result, or my favorite experimental result, that does not agree with the standard model prediction. The so-called anomalous magnetic moment of the muon. Maybe I show you first this nice cartoon here, which is the sketch of the experimental measurement, what is done. We start out with some protons, they hit a target, it gives you pions, the pions decay to muons, indicated by this little cones and the arrow here. And the cone indicates the direction of the spin, and then we see we need the direction of the spin and the direction of flight. And the direction of the spin and the direction of the flight should be aligned. Now, the muons are kept in a storage ring, and here they circulate, and at some point we know muons are not stable, they decay. A muon decays to an electron and muon neutrino. Yeah? We can't see the neutrinos, but we can see the electrons, and from the direction of the electron we can infer about the spin of the original muon. Now, I've written down here in a more mathematical way the coupling of the muon to the electromagnetic field. We need an electromagnetic field to keep the muon here on the circle. So the electromagnetic field, again, depicted here by this A mu, and then this is a muon, and this is a muon. And this is the normal term that we would naively expect in our Lagrange density, the normal coupling between muon, G mu, muon, A mu. But there's another contribution depicted via this other term here. I'm not going to too many details. This F2, and this F2 is a kind of deviation from the naive expectation. Yeah? How the spin behaves with the direction of flight of the muon, and this is called the anomalous magnetic moment of the muon. This one can calculate. People have calculated it. They have calculated to something like 10 or 11 digits. And then what they found is that there is a deviation. Yeah, you see here, 10 digits or so. This is the experimental result. This is the several theoretical evaluations, and we can see that there's kind of, wrote here, this was an evaluation from last year, 3.7 sigma deviation between the experimental and the theoretical prediction. And this is very persistent over all the, let's say, last 10 years or so. You can see in this, here on the right-hand side, this is the current experimental uncertainty. There is a new experiment ongoing as we speak. They are taking data as we speak, and they're even evaluating the data as we speak, and there should be a new experimental result later this year somewhere. Yeah? And in the end, with this experiment, which is now taking place at Fermilab, before it was at Brookhaven Lab, now at Fermilab, they hope to get from this experimental uncertainty to this small one. Yeah, to get to a fourth of the experimental uncertainty, meaning the overall uncertainty would shrink by a factor of 2 or so. And this would.
What is experimental and what is theory?
Oh, sorry. This is experimental. This is the experimental central value. This is the experimental uncertainty. In the future, they hope to get there, but of course we don't know where the central value will be of the future experimental uncertainty. And these are the several theory evaluations with their respective uncertainty.
Why are there these errors in the theory evaluation?
Well, there are several sources of uncertainties. You calculate it up to a certain order in your perturbation theory, but then some orders are missing. You have to estimate what is missing. And then there is one part of the theory prediction, which again you take from experimental data. I think I have it on a slide here. Yes, it's particularly, well, there are two pieces of predictions, and in particular this one here. Here we have a muon coupling to the electromagnetic field. And what can happen is that here you have a photon exchange, and the photon in the second order loop has a quark running around. And this is proportional to the log of the quark masses. But the quark masses we don't know. Yeah, the light quarks give the problem. Yeah, we don't know what is the mass of the U quark exactly, the D quark, the S quark. This is very complicated. And therefore this piece here is taken from an experiment where you imagine you produce here a photon, and then the photon decays to quarks or so. This is a piece of experimental information that is plugged into a theory calculation. And this can be done in various ways. And therefore, here we have various theoretical
but there is one which is not error bar.
I think it, no, sorry. It has an error bar, it's just not visible here. Yeah, you can see here a little bit. No, all have error bars. All have more or less comparable error bars. Yeah. Thanks. No, they all have this uncertainty. Anyway, so this is one very nice example where we calculate very, very precisely, and in the end we see something does not really fit. Yeah? And we will see how this works out, particularly when we have the new measurement, or the new uncertainty. As I said, this year we can hope for the same experimental uncertainty, then combining with the other one, we'll shrink the uncertainty by a factor square root of 2 at least, and it will get very interesting.
And given this expectation for the experimental side, what is going to be, if it is confirmed, what is going to be the discrepancy in sigmas?
7, yes.
Okay.
Yeah, no, it's not written here, but it's correct. It's about 7. Because, as you can imagine, this shrinks by a factor of 4, but then you still have the theory uncertainty, and this overall will make 7. Good. So, let's see how this develops. Now, I told you about fact number 1. We have discovery, we have a standard model like discovery, but fact number 2, standard model cannot be the ultimate theory. And there's only one possible conclusion out of these 2 facts, and the conclusion is that the Higgs boson we've seen can by no means be the standard model Higgs boson. This is not possible, because we have not the standard model, we have something more than the standard model. But, of course, this is also not the question that we are really after. The question that we're really after is, does this BSM physics that must exist, does it have any relevant impact on our Higgs? Can we see something from the Higgs and infer something about the BSM physics? And if so, which model might be favored? And again, as I told you before, in order to analyze this, we have to look for the changed properties, and we have to look for additional Higgs bosons. How am I going with the time? Good. Now, there are many possible models with extended Higgs sectors. I don't know. I have the answer here, unfortunately. But so if you have your favorite model, picture it in your head. We can have the standard model with an additional Higgs singlet. We can have models with 2 Higgs doublets. We can have supersymmetry. We can have supersymmetry with more Higgs particles around. We can have triplets. We can have BSM models without extended Higgs sectors, but with other additional particles, which then via quantum correction again change the properties of the Higgs that we've seen. Yeah? So all this can happen. And now you may ask, so, I mean, you have only very limited time. Yeah? What do I do with my precious time? Which model should I work on? And, well, let's take experimental data as a guidance. I listed here, well, I go to a few more things in a little bit more detail as time permits. Some recent measurements, and I mentioned here the top quark mass, I mentioned the Higgs boson mass, I mentioned Higgs boson couplings, and I mentioned dark matter properties that we've inferred from astrophysical measurements. These are all more or less recent measurements, and if one looks at very simple realizations of supersymmetry, one finds that very simple SUSY models predicted correctly the top quark mass, the Higgs boson couplings, and dark matter properties. And I find this very remarkable. And you can ask me details about this later. Yeah? At least I think it's very good motivation to look at this model. And if you are not convinced, if you say, but SUSY is dead, I don't know whether I can come to this because of time, but I have this part where I answer the question why SUSY is not dead. Just a very few words, because I understand that probably many of you haven't heard about supersymmetry. So this is just one slide about the very basic fact. Supersymmetry is a symmetry between bosons and fermions. Meaning, we have the SUSY operator, this transformation, applied to a fermionic state, you get out a bosonic state, or if you apply the SUSY operator on a bosonic state, you get out a fermionic state. This is the idea of supersymmetry. Or, to give you a better example, we have here a top quark. We apply the SUSY operator and we get out a top, but not a fermionic top, a scalar top with the spin 0, which is called scalar, which is the SUSY partner of the top quark. Or we start out here with the gluon, spin 1, we apply the SUSY operator, and then we get out the SUSY part of the gluon, the gluino, with spin 1/2, yeah? So from boson to fermion. Effectively means that each standard model particle has its SUSY partner. Yeah? This is what it means. It also means that if the theory, if this symmetry was fully, well, let's say unbroken, that's how I call it, if it's unbroken, then the scalar top and the top must have the same mass, the gluino and the gluon must have the same mass. I wrote down here the electron and the SUSY partner, the scalar electron, must have the same mass. And we know that this is not true. We have not seen these particles, so this can't be true. This means that the theory, what we call, is broken, and this is done by introducing additional mass terms for the new supersymmetric particles to make them heavier than the standard model particles. This may look artificial, but in most theories this kind of additional mass terms arise naturally. I will not tell you how and why, but this happens naturally. And so SUSY particles are made heavy in a very simple way, and you can put them at, I don't know, 100 GeV, 1 TeV, 10 TeV, whatever you like. Now this is the basic idea of supersymmetry. I'll skip this, and maybe I'll just show you this cartoon here. Again, this is the standard model, the quarks, the leptons, the gauge bosons, and again, without too many details, we don't have one Higgs particle, but we have 5 Higgs particles here. We have not one complex doublet, we have 2 complex doublets. Again, you can ask me this later. And we have 5 physical Higgs bosons in our standard model part. And now comes the SUSY part. Yeah? So the quarks are accompanied by the scalar brothers or sisters, yeah? The scalar quarks. Then here we have our leptons with spin 1/2, and here we have the scalar leptons with spin 0. We have the gauge bosons with spin 1, the SUSY partners with spin 1/2. We have the Higgs bosons with spin 0, and the SUSY partners with spin 1/2. Yeah? And as I said, these particles are made heavy by introducing mass terms, and effectively, even in the simplest realization, just to make you aware of it, if one is completely naive, this would introduce about 100 free parameters. And you may say, this is complete bullshit, yeah, because there's no theory that describes nature with 100 free parameters. And you're absolutely correct. And we can again discuss how this is handled, it's not even a way out, how this is treated, how this is solved in more realistic theories. Yeah? Okay. But in general, this is the minimal supersymmetric extension of the standard model, the minimal supersymmetric standard model, MSSM. Yeah? Standard model piece, and here the SUSY pieces. Just to show you what SUSY does for us, I told you, the hierarchy problem. Now what happens? Well, we have these new particles. Yeah? We have the fermion loop. You remember the fermion loop gave the problem. Now we have also a scalar loop, yeah? A bosonic loop here, which is depicted here or with this one. And if one looks at it, one finds that this loop contribution, apart from the different mass of these particles, exactly cancels the contribution of the fermion, of the top quark, for example. Yeah? This contribution that went up to 10 to the 13 GeV kind of disappears, and what remains is something that is proportional, the correction is proportional to the mass differences between the fermionic particle and the bosonic particle. So SUSY solved this automatically. And this was the original motivation why supersymmetry was introduced to particle physics. People realized, we have these bosonic partners, they give an additional contribution, we know that they have a different sign in the contribution, and then they cancel and everything works out. This was the original motivation why SUSY was interesting for particle physics. Dark matter, there is one particle which is the effectively, most cases, to make it simple, the supersymmetric partner of the photon. The photon, the massless spin 1 boson, the supersymmetric partner, spin 1/2, massive but neutral, which is depicted with this symbol here, the chi tilde 0 because it's neutral, and then 1 because it's number 1 out of 4, the lightest one. This is the so-called lightest neutralino, which is a perfect dark matter candidate. It has all the properties that you need for dark matter. And in fact, if you calculate the dark matter density of this particle in the early universe, you find out that it's order of 1. What we need in reality is order 0.1. Then there are mechanisms which can be realized how to get you from 1 to 0.1, but effectively it works out. Yeah? Automatically, this particle, the SUSY partner of the photon, is a stable particle which has all the right properties and gives you effectively the right density without invoking any magic or so. Yeah? So this also works. Unification of forces. I put here this nice plot, which is already quite old. Left-hand side, we have 3 forces in the standard model. Electromagnetic force, the weak force, and the strong force. They have been measured. The coupling strength have been measured. 1, 2, 3 have been measured. And now there's a method how to scale them, how they behave at higher energies. They have been measured here at the electroweak scale where we live. But we can extrapolate how these couplings behave at higher energies. And they don't stay constant, they change. Some grow, some grow, this is the inverse. Some grow and some become smaller. And if you think that we want unification of forces, not Ivan, Ivan is shaking the head. They should meet in one point, and then we have unification of forces. In the standard model, they do not really meet. Yeah? They become close, but they do not really meet. Now, in supersymmetry, and this was discovered long after the model was defined. Yeah? It was not designed to do this. What we see here are they bend a little. This is where the SUSY particles play a role. And then we find that indeed they meet with very good accuracy here at something like 2 times 10 to the 16 GeV. Yeah? So here we have a natural unification of forces at what we call the grand unification scale, 2 times 10 to the 16 GeV. What does not work out in the standard model works out naturally in the MSSM. Very nice. And finally, the anomalous magnetic moment of the muon. Also here we have additional SUSY particles in the coupling of the muon with the photon. And if one works this out, one sees, well, this is the range that our SUSY particles can give us in terms of 10 to the minus 10, between minus 100 plus 100 times 10 to the minus 10. And this is about the exponential discrepancy that we have, and this is perfectly in the range. So SUSY also can perfectly explain this kind of discrepancy. Yeah? In fact, we can use this discrepancy to set limits on our SUSY particles, but this would be a different action. So also this works. And this is what I said, SUSY comes to rescue. All of the points that I listed before, SUSY helps or even solves the problem completely. I don't know, I should probably come to an end, right? I will come to an end. Is SUSY dead? And you may know Mark Twain. But then you say, yeah, but the experimental results, I mean, there's nothing. Yeah, we haven't seen anything. So SUSY is dead. Well, this is one of the plots produced here by Atlas, not because we are CMS, this is just coincidence, where we have all the upper limits on the particle masses from the searches. But there's another plot which looks very similar, which is this one here, also from Atlas, coincidentally. This is other models, other BSM models, and these are also the limits, yeah? And so SUSY is exactly as dead or alive as any other BSM theory, yeah? And then, coming back to my original argument, one should focus on the theoretically most appealing one, to use the valuable time that we have in a good way. And again, one can list here all the nice things that SUSY does for us. But let me stop with one thing. This is the last point I will make, and then I conclude. As I said, SUSY comes to rescue for the anomalous magnetic moment of the muon via these new particles. Yeah? So what particles do we have? For example, we have here a scalar muon. This is a scalar muon, the SUSY partner of the muon. Or we have a scalar neutrino, the SUSY partner of the neutrino. And then here we have the charge units, the SUSY partners of the W, etc. Yeah? So we have electroweak SUSY particles, as we call them. Electroweak SUSY particles that do not interact strongly, but only with the electroweak force. If SUSY exists, it should explain G-2, the anomalous magnetic moment of the muon. If SUSY exists, it should do this job. And this means light electroweak SUSY particles must exist. This is my conclusion. There are searches for these light electroweak SUSY particles, which cover some of the parameter space. Again, I will not go into details, but
I open a parenthesis. Aurelio is this Friday coming to talk about searches for new physics at
very
the
good. So he will explain
discussed.
how this works. I just want to tell you there are these searches. They have to be interpreted with some care. Normally, the limits that you see are not really valid because they make some assumptions that are not fulfilled in nature. Anyway. If there is SUSY, yeah, this is where to look. Look for light electroweak SUSY particles, they must be there. Good. With this optimistic word, let me conclude. The Standard Model is a highly successful theory. However, the Standard Model fails to explain or include gravity, hierarchy problem, unification of forces, dark matter, neutrino masses, G-2 with the muon, and some others that I did not mention. Many BSM models exist. Supersymmetry has the best features. It paves the way, I did not explain this, but it paves the way to include gravity via string theory. It solves the hierarchy problem. It unifies the force. It is a natural dark matter candidate. There are some models that naturally include neutrino masses, and also G-2 of the muon is easily fixed. Looking at the experimental data, SUSY is as alive or dead as any other BSM theory. But it's the only theory with all these nice features. I'm not aware of any other theory that has all these nice features. And if it exists, there should be light electroweak SUSY particles, and this is where to look. Thank you very much.
Lo de conclusinos, ¿es un typo o es de formación profesional?
Es a propósito, obviamente.
Me parecía.
Por si acaso, ese es un workshop que organizo aquí cada año, y este año 16 de 20 de septiembre, para los aficionados del Higgs, ¿ya? Con Gervasio y Alicia como co-organizadores, como dicho aquí, y si tenéis interés podéis mirar a la página. ¿Celso?
Sí, tengo una pregunta que igual no debería saberlo. La única partícula descubierta como spin cero escalar es el bosón de Higgs, ¿no?
Correcto.
Bien, si aparece SUSY aparecerán muchas partículas escalares.
Sí.
Pero vamos a ver, el electrón tiene spin cero.
Sí.
¿No puede tener spin 1?
No. Bueno, no es obvio, ¿ya? Puedes pensar, tengo mi partícula de modelo estándar con spin 1,5 y el partner supersimétrico tiene spin cambiado por 1,5. ¿Por qué no es un electrón con spin 1? Pero si miras más a la construcción, cómo funciona, puedes ver que solo un multiplete con un spin 0 y spin 1,5 funciona. El otro no. Ya, para los fermiones tenía una... Espera. Aquí. Standard Model Spin 1 fermions, tenemos un multiplete siempre en spin 0 y spin 1,5. Si empezamos aquí con spin 0, obviamente solo podemos ir arriba y aquí tenemos que ir abajo. Pero ese es un caso que no está claro, así por mirarlo, pero si lo miras en más detalle puedes ver que solo esa es la solución. ¿Ya?
Tengo una pregunta que puede que sea más psicológica que otra cosa. Enseñaste esta gráfica tan bonita de la masa del Higgs y las diferentes ramificaciones de las de los decaimientos, gracias.
Sí.
Y dices que cae justo donde mejor sería que cayera. En física habitualmente cuando la naturaleza te dice que algo está donde mejor es, aparece un aguafiestas que te dice que eso es un efecto selección, que tal. ¿Hay algo de eso entre vuestro negociado o no?
Había 1 o 2 artículos, pero yo creo que es casualidad.
Es así.
Para mí sí, ya no veo nada detrás. Existe un plot, no lo tengo, pero lo vi hace tiempo, masa del Higgs, y aquí el producto de todos los branching ratios es una curva así y tiene su máximo exactamente a 125. ¿Ya? El producto de todos los decimamentos a 125, pero yo creo que es casualidad. Tenemos suerte. ¿Ya?
No sé si puedes explicar muy brevemente. Has mencionado que Susi puede explicar muchos de los problemas que has mencionado, te has centrado en 3 o 4, pero ¿podrías decir un poquillo cómo puede ayudar a no incluir la gravedad?
Es un poco complicado. Tienes que mirar a su simetría como teoría de gauge local, y en ese momento llegas a teorías que se llaman supergravity, que del otro lado también está realizado en las teorías de cuerdas. ¿Ya? No hay una solución. No digo que existe una teoría de gravedad que se puede incluir, pero gente está trabajando en eso para explorar este camino. ¿Ya? Todavía no hay solución. El problema con la gravedad es que el gravitón tiene spin 2, que no se puede, no puedes escribir una quantum field theory, ¿ya? Con eso. Pero si las partículas elementales no son como un punto, pero tienen una dimensión y extendidos, este problema parcialmente desaparece y puedes pensar cómo escribir una teoría conjunta con eso. Pero, como he dicho, no hay, por eso he dicho, paves the way, ¿ya? Pero no incluye gravedad o algo. ¿Ya?
A lo mejor también el problema es querer unir la gravedad a las otras 3, ¿no? A lo mejor es suficientemente diferente de las otras interacciones como para que no haya que...
En el final es lo que queremos, ¿ya? Que hay una fuerza y no 2. ¿Quién sabe? Quizás nada, bueno, que es sorprendente o no sorprendente, que es bonito que vimos una unificación de varias fuerzas. ¿Ya? ¿No? Y por eso creemos que podemos continuar en este camino, por eso. ¿Ya? Y cada vez la teoría se pone más elegante o más sencilla, ¿ya? Si hay una unificación. Si en el final tenemos 1 o 2 fuerzas.
Bueno, simplemente porque la naturaleza de la gravedad es un poco diferente a las otras interacciones.
Es diferente, pero en la escala Planck tenían la misma fuerza.
Sí,
casi, sí, tampoco es muy artificial en este sentido.
La escala de energía.
Ya, bueno.
Una pregunta un poco así. Cuando dices que hay divergencias con la energía, ¿cómo sabes que esas divergencias son del modelo en sí y no de la teoría de perturbación que estás usando? O sea,
¿estás hablando de WW?
Sí, creo que sí.
Ups. ¿En ese?
Sí.
Ya.
¿Cómo sabes que no es un problema de que no puedes aplicar ahí la teoría de perturbaciones porque estás muy lejos?
Claro. La alternativa, bueno, cuando no sabíamos si existe un Higgs o no, la alternativa a esta solución es que a energías más altas tienes una fuerza nueva, ¿ya? Y esta fuerza nueva arregla el asunto, ¿ya? Una fuerza fuerte que cambia esta curva y que, ¿ya? Para que no sube más. Era otra solución, mucha gente trabajaba en eso, ¿ya? Pero, como has dicho también, es una teoría no perturbativa. Es muy difícil hacer cálculos o predicciones concretos. Puede ser que la naturaleza es así, puede ser, pero si queremos una teoría que es perturbativa, esa es la solución, con el Higgs. ¿Ya? Y ahora sabemos que con el Higgs probablemente funciona. ¿Ya? Ahora lo sabemos. Antes ha sido, bueno, una pista, ¿ya? Pero nada más. ¿Ya? Ahora lo sabemos.
Y una otra preocupación que parecía, aún teniendo el Higgs, digo, el último, con lo de la escala de Planck, había uno que parecía...
Hablas de...
Espera.
De eso. Sí.
¿Cómo sabes que no es un problema de la teoría de perturbaciones, que hay alguna cosa extraña por ahí? Que diverja.
Eso es... Bueno, este proceso pasa a la baja energía, a nuestra escala electrónica. ¿Ya? Tienes un Higgs y tienes simplemente su masa y nada más. Pero y luego haces este cálculo y el cálculo tiene este resultado aquí abajo. Si dices, bueno, si mi teoría no es perturbativa, ya, puedes decirlo, pero en ese momento se acaban las predicciones y nada funciona. Puedes hacerlo, pero no te ayuda mucho. Si dices, teorías perturbativas funcionan muy bien y vemos que hay cálculos con alta precisión, ¿ya? Con muchos bucles y todo funciona. Y ¿ya? Si tú haces un cálculo a 2 loops, ¿ya? Y en el final llegas a un resultado que tiene sentido, que todas las divergencias, todos estos términos se cancelan, es increíble, ¿ya? Que funciona. Y la teoría es también bonita en este sentido, ¿ya? Pero podría ser que el mundo funciona de otra manera y este argumento no es válido. También es posible. Pero hasta ahora todo parece como perturbativo.
Quería preguntar, que es un poco parecida a la que iba a hacer yo. En realidad, este tipo de problemas del strong coupling aparecen en mecánica estadística también, de sistemas con strong interactions. Entonces, claro, la pregunta que uno se hace de la forma en que se resuelven altas energías es siempre asumir que la física del mundo es tal que el punto que interesa, la teoría buena, es una teoría perturbativa. O sea, que es accesible, que el punto al que buscamos de la naturaleza,
sí,
al final la vamos a encontrar de forma
pero creo que es un poquito distinto.
Pero es que en la realidad no es así. En la realidad en otros campos no es así. Existen perfectas teorías iguales que las que tú estás formulando en materia condensada, donde el punto físico no es un punto perturbativo y no se puede alcanzar por métodos perturbativos. Entonces, sí, siempre existe, si no hay algún criterio más general, más actual, ese criterio por el cual el argumento es voy a introducir un campo más que me resuelve el problema, me hace posible hacer la teoría perturbativa a expensas de introducir más y más parámetros. Entonces, un poco lo que has dicho tú.
Ya, claro, aquí introducimos, sí, cierto.
Pero,
no sé, no es algo que creemos o algo, sabemos que el modelo estándar funciona bien como teoría perturbativa, ¿ya? Pero en este momento, aquí, tiene un problema.
Sí.
¿Cómo solucionarlo?
Sí,
¿ya?
porque es que, por ejemplo, la supersimetría, es difícil imaginar que una teoría con 100 parámetros no es capaz de explicar muchas cosas. O sea, quiero decir,
podríamos hablar de los 100 parámetros.
Te voy a hacer la pregunta. Tengo 5 o 6 problemas que digo que son problemas de teoría estándar. Amplío la teoría, una teoría de 100 parámetros, con diferentes interacciones, porque no en todas esas 6 explicaciones, esos 6 problemas que has contado, intervienen las mismas partículas, supongo, supersimétricas. Tienes diferentes situaciones que son las que tienes que tener en cuenta para explicar los diferentes, por ejemplo, para explicar Dark Matter, con el ejemplo que has puesto, no usas las mismas partículas que usas para el momento magnético, ¿no? La anomalía del momento magnético. Es fácil pensar que si construyes la teoría con un poco de inteligencia y 100 parámetros, puedes ajustar los parámetros sin que interfieran, de manera que podrías resolver varias de esas. Esa es un poco la curiosidad, ¿no? Como esos parámetros que tenéis libres se fijan como en función del problema que quiero explicar, y luego puedo comprobar que efectivamente tiene ese valor y no tiene otro, de alguna manera experimental o con alguna otra anomalía que pueda comparar? ¿O usas diferentes, o sea, valores de los parámetros que explican en el momento anómalo del muón, pero no intervienen, por ejemplo, en el dark matter? Entonces, pues son independientes, no fijarlos de forma arbitraria.
No hay una respuesta final a tu pregunta, ¿ya? Si lo sabíamos, perfecto, pero...
De acuerdo.
Pero, para dar un ejemplo, he dicho que tenemos la unificación de las fractas. Así, en su simetría es muy normal, natural, asumir una teoría en esa escala de GAT a 10 a 16 Ref, definir la teoría allí, y allí se puede definir la teoría con muy pocos parámetros, 3, 4 parámetros, y luego todos los parámetros a baja energía simplemente puedes calcular en función de estos 3, 4...
¿Los extrapolas de forma perturbativa?
Sí, con renormalization Ruby equations.
Sí.
¿No? Ya. Y en ese momento puedes hacerlo y puedes explicar, o casi todo funciona tan bien en este tipo de teoría, ¿ya? Como con los parámetros libres. Y así tienes muy pocos parámetros libres, 3, 4, y todavía funciona bien. ¿Ya? Esa es una posible respuesta. O en final, lo que te faltan son 3, 4 parámetros que tienes que ajustar en todos para resolver tus problemas. ¿Ya? Pero es cierto que las pistas que tenemos para física BSM realmente afectan a sectores distintos. ¿Ya? El neutralino no es el mismo como el tope escalar, por ejemplo. ¿Ya? Por eso. En este sentido tienes razón, pero también en las teorías definidas en la escala GAT todavía las cosas funcionan.
Y tenía una segunda pregunta.
Yeah.
Normalmente en la teoría estándar las partículas portadoras, las partículas que portan interacción son bosones. En los compañeros supersimétricos se convertirían en fermiones. Yo me preguntaba si esos fermiones siguen siendo portadores de interacción o se comportan como...
Sí, esa pregunta mucha gente hace. Yo no lo veo así. Tenemos 4 fuerzas o 3 fuerzas en nuestro modelo con sus partículas que transmiten esta fuerza. Nada más. Tenemos los partes simétricos que simplemente existen como intercambiar algo, pero si piensas en una fuerza, en un campo, eso tiene que ser un bosón.
También
sí, eso no cambia. La fuerza electromagnética está hecho por el intercambio de los fotones, punto. No los fotinos, ¿ya? No los neutralinos, nada. Eso simplemente son partículas adicionales que existen en la teoría. Pero no debes verlo como una fuerza adicional.
Sí, yo tenía una pregunta. En los últimos años ha estado muy presente el argumento de naturalness y concretamente en las búsquedas de Stokes, en una de estas partículas supersimétricas, pues el argumento de naturalness parece llevar a que debe de haber un Stokes del orden de un TeV, en la escala de un TeV. Y ahora experimentalmente, a pesar de que es verdad que los límites que ponemos experimentalmente hay que cogerlos con mucho cuidado, pero es verdad que estamos empezando a rebasar más o menos 1,2 TeV. Es posible que ahora en el LHCP se muestre algo un poquito más avanzado, quizás. Y bueno, mi pregunta en general era ¿cuál era tu opinión acerca del argumento de naturalness y qué piensas sobre eso?
Sí. Claro, nuestra esperanza era o es que las partículas tienen que tener una masa, decimos, un TeV o algo, ¿ya? No está muy claro. Ese es el problema de este argumento, es que no está muy claro. Si al final descubrimos stops con una masa de 3 TeV, hipotéticamente, todos esos argumentos desaparecen. Nadie tiene más interés, ¿ya? Solucionado, ¿ya? Así no sabemos qué esperar concretamente, ¿ya? Es cierto para mí que la teoría pierde su belleza si no encontramos nada abajo de varios TEF, ¿ya? No podemos solucionar los problemas, ¿ya? Materia oscura es difícil, G-2 es difícil, no parece natural, estoy de acuerdo, ¿ya? Es un argumento complicado. Todavía creo que, bueno, he dicho por razones experimentales que partículas electroweak tienen que existir. Los stops por naturalness también se espera en orden de un TEF, y especialmente los límites a los stops son bastante bajos todavía, ¿ya? Están en orden de, no sé, 500, 600, 700 GeV, depende de las otras masas, pero también todavía más baja. Y hay mucho espacio de explorar que todavía parece bien o normal, ¿ya? Pero el problema es que no hay ninguna predicción completamente clara. Con el Higgs sabíamos que tenemos que esperar, ¿ya? Que algo bajo de un TEF tiene que existir de una u otra manera para solucionar, por ejemplo, el problema de W, ¿ya? Tiene que existir. Ahora no tenemos algo tan claro. ¿Ya?
Una pregunta. En relación al problema de la materia oscura, bueno, pues
Sí.
si nos da un candidato, ¿qué pasa con todas las otras partículas que son supersimétricas? ¿No contribuirían o son muy inestables?
Sí, no lo he dicho en detalle, para mí es tan claro que no lo digo. Es cierto, solo la partícula más ligera supersimétrica es estable. Todas las otras se desintegran rápidamente, ¿ya? Y así, solo la partícula más ligera puede ser materia oscura, o tal vez también el partner supersimétrico del gravitón. El gravitón también es un candidato, ¿ya? Pero es otro asunto. En el universo joven, con todas las interacciones, también las masas de otras partículas tienen su papel. Por ejemplo, no lo mencioné, a ver. Aquí. He dicho que normalmente la densidad es orden 1 de tu neutralino, ¿ya? Entonces necesitamos un mecanismo en el universo joven para reducir la densidad de materia oscura. Y hay varias posibilidades como reducirla. Por ejemplo, si este neutralino está muy cerca con su masa con el partner supersimétrico del tau. El tau escalar, ¿ya? En ese momento puedes tener una aniquilación a modelo estándar de estas dos partículas, ¿ya? Te dice algo sobre la relación entre la masa de materia oscura y el siguiente más ligero, en este caso el tau escalar. O que puede pasar en el universo joven es que tienes dos partículas de materia oscura que se aniquilan para formar un Higgs pesado del modelo y luego va a modelo estándar, ¿ya? Este Higgs pole annihilation. ¿Ya? En este momento la masa del Higgs pesado es más o menos 2 veces más grande que la masa de materia oscura. Así hay relaciones entre los parámetros que tienes que encontrar para llegar a la densidad que hemos medido. ¿Ya? Y no es solo esta partícula que vive solo, pero la relación de esta partícula con otras partículas es importante para llegar a una densidad que está de acuerdo con las medidas.
Y una cosa más, en relación a la energía
Sí.
oscura, ¿sí puede decir algo de energía oscura? ¿Alguna predicción?
Energía oscura no soy consciente de algo específico de supersimetría. En general, creo que todo muy especulativo sobre energía oscura. No voy a decir más. No, Iván, primero. Ya.
Sí, a ver, el tema es, a mí me gusta mucho hacer analogías de estado sólido. Entonces, suponiendo que tenemos muchos Higgs, ¿no?
¿Tengo muchos?
Muchos Higgs, ¿no?
Muchos.
Supersimétricos adicionales.
Sí, sí.
Entonces, tendríamos, digamos, transiciones de fase, rupturas espontáneas de simetría para cada uno de ellos. No.
No.
Tendríamos
una transición de fase solo.
Una transición.
Porque solo tenemos, bueno, tenemos dos LEFs, tenemos dos dobletes de Higgs, ¿ya? Y tenemos así dos LEFs, pero es realmente una transición de fase. Es un parámetro, no es
un potencial.
Sí, un potencial y
un único potencial.
Ya, no una transición de fase para cada Higgs, no debes pensarlo así no funciona, es una transición de fase.
Vale.
Que es, quizás puedo mencionarlo aquí, existen teorías supersimétricas en que esta transición de fase es de primer orden y te causa ondas gravitacionales.
Claro, eso es lo que iba a preguntar. O sea, lo que iba a preguntar es que si tienes, si lo imagino un condensado de Higgs, el famoso condensado de vacío, ¿no? Que está aquí. Entonces, eso es un cambio tan brusco en la energía del universo, en cómo se reparte la energía del universo, que tendría que haber tenido alguna huella cosmológica. Algo tendría que... O sea, porque de repente cambió de fase de manera bestial, se liberó una cantidad de energía bestial, porque es
Bueno, depende no solo depende si la fuerza, pero como decirlo, hay transición de fase primer orden y segundo orden, y solo las transiciones de primer orden te causan ondas gravitacionales en el universo joven que todavía existen, ¿ya? Que es como un fondo de ondas gravitacionales que podría existir. Y hay cálculos que te dicen, wow, si esta teoría, por ejemplo, con dos dobletes de Higgs, si eso es cierto, con el DeSigo, o como se llama, ¿ya? O LISA tal vez no es bastante fuerte, pero DeSigo es del rango correcto. Hay una posibilidad que vemos este fondo de ondas gravitacionales causado por la transición de fase en el universo joven. Eso es cierto, ¿no? Hay esperanza y es muy fascinante para mí. Una relación entre estas ondas gravitacionales y el sector de Higgs, el modelo BSM.
Y luego lo que yo no entiendo, es ignorancia, es la temperatura de esa transición de fase no es tan alta, ¿no?
No.
Entonces, ¿por qué no vemos, por ejemplo, en Alice,
Yeah.
¿por qué no vemos que el W y el Z pierden la masa?
No sé si llegamos a esta temperatura ya, creo que estamos todavía bajo de esta temperatura, pero tampoco puedo decirte cómo se comportarían en ese momento, eso simplemente no sé.
Deberíamos ver bosones sin masa. Deberíamos
Ya, pero...
Y W sin masa, ¿no? O sea, bueno, los ves. ¿vale?
Efectivamente, si vas a energías muy altas, efectivamente no tienen masa.
Y
¿ya?
esa energía es del nivel electrodébil, no es tan alta, o sea, no lo entiendo, hay algo que no me cuadra.
Ya, pero creo que, yo tampoco sé los detalles aquí, pero creo que es simplemente pensar, si vamos a la escala electrodébil, estamos encima de este límite y todo es siempre, todos los cálculos están a temperatura cero. Todos los cálculos asumen temperatura cero. Así.
Vamos a dejar la última porque hay que dejar hueco a los alumnos.
Sí.
¿Vale? A ver,
Yo tengo una pregunta que es como doble, pero...
Eso es una trampa.
No os he hablado nada de todas estas partículas que pueden aparecer en un modelo de supersimetría sin masa, pero que pueden jugar un papel y no sé, espero que serían muchas relativistas, ¿no? En tiempos...
Pero ¿por qué dices sin masa? Todos tienen masa.
¿Todas tienen masa?
Todos tienen masa, sí.
No hay ninguna que no tenga...
No.
No,
Porque, para empezar, tienen la masa de la partícula del modelo estándar. Y encima ponemos masas adicionales que rompen su sí, que lo hacen aún más alto, aún más pesado.
Bueno, en cualquier caso, a partir de una cierta energía, cuando vas para atrás del universo, se van a comportar como relativistas.
Sí.
Porque es
Sí,
una
claro,
son pequeñas,
ya.
se comportan. Entonces, desde el punto de vista cosmológico, hay límites muy fuertes al número de especies relativistas que pudo haber en el universo. Entonces, como mucho, hay tres. Hay unas cotas muy fuertes en el número de...
Pero eso solo funciona con hablas de neutrinos, por ejemplo.
Claro.
¿Ya?
Pero bueno, no, y más que neutrinos, especies relativistas.
Pero solo puedo decirte que la gente hicieron este cálculo y con las masas y todo funciona. No hay ningún problema en general en este sentido. No me preguntes los detalles porque no lo sé, pero sé que la gente lo miraban y
que no había problemas.
Sí, sin problemas.
En principio son cercano a 3 más.
Ya, pero en el modelo estándar también tienes muchas más partículas, ¿ya? ¿Y por qué no tienes ese problema en el modelo estándar?
Bueno, son inestables muchas de ellas.
Ya, pero SUSY también.
Ah, son inestables, ¿no?
Sí.
Inestables son
Todo se desintegra. No.
Y luego, para acabar, no has dicho nada de los neutrinos estériles, que también pueden jugar un papel. No sé cómo aparecen, si nos puede recordar un poco, eso está dentro de... ¿Es SUSY eso también?
No
tiene nada que ver.
No tiene nada que ver. Neutrinos estériles tienen nada que ver. Es otra explicación para una de las cosas que vemos en las oscilaciones de neutrinos, posiblemente, aunque para mí ahora todo parece que funciona o está en contra de neutrinos estériles, pero es algo distinto, no tiene nada que ver con lo que...
Bueno, vamos a darle las gracias de nuevo y hacemos